So how is the Hardy Cross assignment going? Homework 5.
Great. Fantastic.
Oh, okay. That sounded sarcastic, actually. That was a little too much enthusiasm. Still working on it, it sounds like. All right. All right. That's fine. You've got 2 days to finish it, so that's tons of time. If you have any questions, let me know, because as I've already emphasized, I sure love these Hardy Cross spreadsheets. So let me know if anything comes up. Water hammer and surge tanks, you can ask me about that too, but it's the Hardy Cross problems I'm real excited to hear about. Today we're going to be talking about pumps. If you are following along in the book, then this is related to Chapter 9. And there's also an additional practice problem for Hayes and Williams, which honestly I'm not sure if we'll get to because I've added a couple of new videos to today's lecture that I haven't previously included. So probably we won't get to that Hayes and Williams equation practice problem today. But any announcement questions before we start discussing pumps? Pumps can be very simple and they can be very complicated, and the thing that the simple and the complicated pumps both share in common is that they exist to add energy to water. That the purpose is to either cause flow where flow otherwise wouldn't be possible, or to increase the rate of flow where water would be flowing naturally. A pump can increase the rate. And the simplest types of pumps are positive displacement pumps. And a positive displacement pump is one type of a positive displacement pump is a screw pump, which you can see looks like a rotating shaft in a trough of water. And just to show you a side view of what that looks like, it could be driven by a motor, or historically these positive displacement pumps were driven by human hands, where the bottom end of the pump is immersed in water, and then the upper end of the pump is going to be discharging water someplace else where you need it. And so if you think about how this would have been used historically, if there was water in a river or in a canal and it needed to be lifted up into the fields, then a farmer would be cranking the pump and it would lift the water, and with each rotation it's lifting a certain volume of water that's trapped in between the blades of the screw and the outer casing of the pump. So if you look at the energy equation, remember that there are 3 basic places that the energy can reside. In this first term, it's the pressure head, and so energy in an enclosed pipe can be represented by the pressure of the water. Z is the elevation term, and then V is related to the velocity of the water. So if we look at the water at location 1 versus here at location 2, the way that this positive displacement pump has added energy is in terms of the Z. It has raised the elevation of the water, and therefore the work that's being done by the person rotating that pump, and it would be a lot of work. Think about it day in, day out. If you're just cranking that pump continually, that would wear you out. But the work that's being done is adding energy to the water by lifting it. So its potential energy is increased. Different types of pumps add energy differently. But in the case of this, where it's open to the atmosphere, it's not pressurizing the water, and the velocity of the water at both of these locations is the same and pretty small. So really the work that's being done is in lifting it. So the weight of the water and the distance that is being lifted is the work that's being done. Now, positive displacement pumps can be a lot of different types, not just that screw pump. A rope pump is something that basically a plug, a rubber plug, or it can be plastic, but some plug that's about the same diameter as this immersed pipe is attached to a rope which is flexible, or it could be a chain, but it's attached to something that's flexible, and you can see as it enters this immersed section of the pipe, the water is forced upward because of the plug. I mean, it may be seeping slowly around the edges of the plug, but presumably it's being lifted at a rate that causes the water to go out this discharge side. And so rope pumps are sometimes seen in the developing world as a way of lifting water out of an aquifer and to give people water for cooking and irrigation and so on. The rest of these pump types would typically be used in conjunction with motors rather than hand cranked. You can see that what they share in common is that with each rotation there's a fixed volume of water that's being discharged, and it's related to the void that's created. So in the case of this internal gear pump, each rotation has a fixed volume, which is the space between the gears and the sprockets. Same thing with the lobe pump. It's rotating and there's just a certain volume of particles that fills the void that's created by that rotation. Peristaltic pumps are pretty common to see in research applications. If you go into a chemistry wet lab, you're likely to see a peristaltic pump, or in medical situations. What a peristaltic pump is, this is like a flexible tube. So think about like a rubber or plastic tubing. And if it's being squeezed together with a roller, it creates a pinch point where the water can't go around it, and as it rotates, it's forcing a certain fixed volume of water to go through the pump because of this pinch point, which prevents the water from going backwards. The same thing with a scroll pump. It's just a certain volume is opened up and then forced through this spiral system, and then it's discharged at the center when it all comes together. So these positive displacement pumps are kind of obscure edge cases that are really only used in rare specialty applications. Far more common would be radial flow pumps. So we're going to look at a video that explains these radial flow pumps, and the way that these work is by increasing the pressure of the water. So remember that there's three places that the energy can be. It can be in terms of increased velocity, increased elevation, and increased pressure. And these add energy by increasing the pressure. So we're going to start off by watching this video. Just what it's talking about so far. So there is a transition between the electrical energy and mechanical energy, and that's being accomplished by the motor. They're about to show you like the exploded view of what's going on inside the motor, and I think it's worth us taking the time for that. I know that you're not an electrical engineer. Back in the early days of our program, civil engineering students had to take thermodynamics and circuits. And so I think that probably very few of you are likely to take either of those classes as a technical elective. But I think it's worth seeing once just the explanation of what's happening inside the motor. Really, as a hydraulic engineer, we're mostly interested in what's happening inside the pump. So people will say pump and refer to the whole thing, but technically pump is just what's taking the mechanical energy and turning it into fluid energy. So it's just kind of maybe a lazy way of referring to the entire thing as a pump, when really it's a motor connected to a pump. All right. Okay, so when you first look at this, it may be a little bit counterintuitive, the orientation of the impeller. They're going to talk about it in more detail in just a moment, but the impeller is, I guess you could think of it as it's flinging the water rather than scooping it. Like the shape of this impeller, they're going to get into a lot of detail about the shape of it, but this was rotating in I guess the way that we're looking at it, in a clockwise direction. And pay special attention to the fact that
creating the rotating magnetic field within the motor,
it's not interchangeable, this impeller, so it's kind of flinging the water outwards and upwards to create that pressure. Watch. I think that's a really excellent video for kind of showing you inside the pump and explaining how the impeller is actually adding energy. And so when I was saying it flings the water rather than scoops it, what I meant is it's increasing the velocity, and then as it hits the volute, it transfers that additional velocity into an increase in pressure. And So there's a suction side where the pressure is low and the pressure side where the pressure is high. And we'll talk about some of the risks that can arise on the suction side of this, this pump. And to avoid some of those risks, sometimes an axial flow pump is used instead. And an axial flow pump is more just like you could think of it as like a submerged boat propeller. And rather than accelerating the water and turning it into additional pressure, this is causing, with each rotation, it's accelerating the water in the direction that it actually needs to be pumped. And so the motor that drives the shaft could be at the surface in an axial flow pump. It could be that like this is submerged in a pipe that's down underground for an aquifer. And so the motor and the impeller of a pump sometimes will be quite some distance away. But the difference in the axial flow is just that the water's flowing in the direction that the shaft is oriented, and it's not changing direction like it would in a radial flow pump. So let's look at this pump, which is sucking water from some reservoir, and it's drawing it through a strainer. And you can see that the water inside of the pipe has some velocity. And here I've just noted that because the diameter at location 1 and location 2 is the same, we can tell just by looking that they've got about the same diameter. So the velocities at these two locations would be the same, both upstream and downstream of the pump. The velocity is the same, and the elevation of the water upstream and downstream is the same. And so the only place in the energy equation that that pump can add energy is through an increase in pressure between the 2 points. The same thing is true for the radial flow pump. But as to the risk that can arise, on the suction side of the pump, remember that the pressure at the water surface is atmospheric, so like 0 gauge pressure. And as you go in the direction of flow, the pressure is going from 0 down into the negative range. And we're talking about the gauge pressure. Of course, the absolute pressure isn't 0, but the pressure is decreasing in the direction of flow, and depending on how long the suction side is, cavitation could occur. And is cavitation something that Dr. Yoon talked about in fluid mechanics? No? Well, we're going to talk about cavitation in hydraulics this semester. And basically, it's a phenomenon that can arise when you get too close to the vapor pressure of water. And if you've got suction and you're approaching the vapor pressure of water, essentially it boils inside of a pump. It can happen. And those little cavitation bubbles that collapse inside the pump can cause damage to the pump. So we'll talk about the risk of cavitation, but the risk of cavitation is associated with suction side pumps that are too long, or if the suction side diameter is too narrow, that's associated with cavitation. Or if there's a big elevation difference between the reservoir that the water is drawing from and the location of the pump, if there's a big delta Z. So that's the risk that we'll talk about a bit further when we get to cavitation. Now, as you'd expect, when you are transferring the electrical energy, I thought I could refer back to the video. If you're transferring electrical energy into mechanical energy and then transferring the mechanical energy into fluid energy, there's going to be some losses along the way. And the video referred to that because it talked about how it has to have a fan to blow air through the electrical motor to dissipate heat. And so all of the energy that was transferred as heat and is being blown out of there, that's lost. So ideally, if we just think about without any losses, then the amount of power that is being imparted by a pump is equal to the flow rate times the unit weight of water times the pump head. And of course, in BG units, we'll have units of horsepower if we divide by 550. In SI units, it's going to have units of watts. Now, the overall system efficiency depends on the efficiency of the motor at transferring electrical energy into mechanical energy, and the efficiency of the pump at converting mechanical energy into fluid energy. And so the overall efficiency is the product of those two. And so the real pump equation is just that the amount of power that's actually added to the water is the unit weight of water times the flow rate times the pump head divided by some efficiency factor. And dividing by the efficiency factor will tell you how much power is required to put into the system to get a certain amount of energy into the water that you desire. So these efficiency factors have values of less than 1. It's usually some decimal. Like a typical efficiency might be 0.80. And so if your efficiency is 0.8 and you need to have 1 kilowatt of energy go into the water, then 1 kilowatt divided by 0.8, you can see that it's going to be more than 1 kilowatt that has to go in as electricity to get the 1 kilowatt of energy into the water. You'd have to put in 1.25 kilowatts of electricity into the motor. So you put in 1.25 kilowatts of electricity, you get 1 kilowatt of energy into the water, and then how much of that energy goes into the pump head, you get out of the flow rate and the unit weight of the water. So pumps don't always act at the same efficiency. They can have varying efficiencies depending on the density of the fluid, the viscosity of the fluid that's being pumped, the diameter of the pump, the speed that it's rotating at. There's a lot of factors that can adjust the efficiency, and the energy that's being lost mostly is dissipated as heat, whether it's heat that's going into the water or heat that's going into the air from the motor. Let's watch another section of video that's going to talk about a pump performance curve. It's basically, this pump performance curve is a description of the flow rate that can be achieved versus the load that the pump is working against. Okay, so I think that the most useful illustration on here is the idea that if you have this pipe vertically oriented, then before any water can come out of the pipe, it has to be lifted a certain distance. And that's sometimes called the cutoff head. It's the amount of head that would cut the flow down to 0. But then if the pipe is horizontally oriented, then it's not having to lift any elevation. It's only overcoming a little bit of resistance in the pipe. So the flow rate is much higher. And so this is called a pump curve, a pump performance curve. You know, this is just an example equation here, the 24.4. That's not like a fixed law or anything. That's just, let's say that there's a particular pump out there where it can lift water to a height of 24.4 meters, and then the decrease of the pump head it can add is related to the flow rate squared. So you can see this second term here related to flow rate gives us an indication of how much the head that's being added decreases as you try to increase the flow rate. So from a pump, you can either have a high flow rate, which is not adding very much pressure, or you can have maybe a medium flow rate and it's adding a medium amount of pressure, or if you have to add a lot of pressure, then there won't be able to be much flow going through the pump. So each pump has its own separate performance curve. This is just an example equation that we're going to use in an example that we want to calculate. And the general notion is that as the head increases, the flow rate goes down. Now, this is called the pump performance curve. There's also something that we can put together called a system curve. And this is, let's say, an environment where a pump is being used. Just for example, what if we were trying to pump water from a low reservoir up to a higher reservoir? And so there's a certain elevation difference between the two tanks, delta Z. And then think about the work the pump is going to have to do is partly related to the elevation difference between the two tanks, and it's partly related to the friction losses as the water flows through the pipe. But then it's also going to be related to the local losses, because you can see that there are a few bends in the pipe as well. So we could make a graphical representation of that, and it's called the system curve. If we wanted to have a graphical representation of the elevation that's being lifted plus the ever-increasing effects of pipe friction and how much energy has to be added to overcome it. So as the flow rate goes up, then the amount of friction that has to be overcome increases. And it's not a linear increase, it's an exponential increase. You'll notice we're multiplying flow rate squared. So here is the term that has to do with pipe friction, the first term here, F being our Darcy-Weisbach friction factor, L is the length of the pipe between location 1 and location 2. 2GA squared, of course, that's just a constant related to the diameter of the pipe, and here is a separate term for D. And then K is the term that refers to the local losses. So there could be valves or fittings or bends, whatever the case may be for our local losses. So how much water is actually going to be pumped in any given time, like what is the flow rate that will be achieved, is the overlaying system curve and pump curve. And so you put the two curves on the same graph, and where they intersect is the operating point. Or in other words, we can solve for Q if we have an equation for the system curve and an equation for the pump curve. So the operating point is just how much flow rate you're going to get and what head is being added by the pump for that given condition. Now, the trick in these sorts of equations is that we don't necessarily know to begin with what is the F value that should be used in the Darcy-Weisbach equation. So we'll apply the fully turbulent flow assumption to simplify calculating F initially, and then we'll later on check the fully turbulent flow assumption and update, if necessary, the F value. So the fully turbulent flow assumption, we're just assuming a really big Reynolds number so that the denominator of that Jane equation only depends on the relative roughness term. All right, so let's try this example where we're trying to find out what is the flow rate that will arise for a system that has a pipe length of 120 meters, and we know the pipe diameter is 250 millimeters. There's a certain pipe roughness, 0.25 millimeters is the equivalent sand roughness. There's a couple of bends and fittings in the system so that the K value is 2.4, and then the elevation difference is 9.1 meters. Now the first thing you should look at is in the pump curve whether the cutoff head is greater than the delta Z. So in the pump curve for this pump that we're going to try and apply to this system, the cutoff head is 24.4 meters. So luckily it's more than the 9.1 meters of elevation we're trying to lift the water. Because if delta Z was greater than the cutoff head, then no water will flow at all. And actually, I had an experience when I was a student. I had a landlord who didn't know about pumps. He just bought a pump and was trying to pump water up to the second story of the building, but the pump was not rated with a cutoff head that would allow him to pump water up to the second story of the building. So you have to have a pump curve where the cutoff head is greater than the delta Z at the very least. So our system checks out, it does. So what we're going to do here is set the two curves equal to each other. I'm going to solve this one on the whiteboard, and hopefully we'll see if we can find out what is the operating point for this system. I'll write the variables on the board here. Okay, so the basic idea is we're going to set the pump curve equal to the system curve, and then solve for Q. That is our solution methodology. And let's create the system curve. So the system curve we get from the environment that the pump is going to be placed in. We know, for example, that the length is 120 meters. That's the length of the pipe, which has a diameter of 250 millimeters. The relative roughness is 0.25 millimeters. The local losses have a K value of 2.4, and the delta Z is 9.1 meters. So that's the height that we're lifting the water. So the cross-sectional area of the pipe, pi d squared divided by 4. For this 250 millimeter pipe, the cross-sectional area is 0.04909 square meters. And so we'll use the fully turbulent flow assumption to estimate our initial guess of F. So the F value in that fully turbulent flow assumption of the Jane equation is 1.325 in the numerator, and then the logarithm of 0.25 millimeters divided by 3.7 times 250 millimeters. And square all of that in the denominator, because we don't know the flow rate, so we won't consider the Reynolds number portion of it. It gives us an initial guess of 0.196, and that's using the fully turbulent assumption. I'll put a little star here because we need to go back later and check that assumption to see if it was valid, and if not, make a slight adjustment. Okay, so now I'm going to put it into our system curve notation. So the system curve formula is delta Z, so 9.1 meters, plus Q squared times our F value 0.0196 times the length, 120 meters, divided by 2 times G, 9.81 meters per second squared, times the area squared, 0.04909 meters squared, and square that. Things are getting cramped. Times the diameter, 0.25 meters, and then plus the sum of the K values, 2.4 divided by 2G times the area, 0.04909 meters squared, and square it. Okay, so all of that inside the brackets there, this one is 198.98. This term works out to 50.76. So my system curve is H sub P is 9.1 plus 249.74 Q squared. That's my system curve. So what the system curve tells us is that as the flow rate goes up, the amount of pump head that has to be added increases as well. Now our solution strategy is to set the system curve equal to the pump curve. Okay, so I'm going to set this curve equal to, let me just erase this. This was 198.98. Okay, so here's our system curve is equal to the pump curve. And the pump curve, this one has 24.4 minus 7.65 Q squared. So system curve is equal to pump curve. They were both in terms of H sub P. So the system curve is equal to the pump curve. And so that is 257.39 q squared is equal to 15.3. You know, if I have 24.4 and I take away the 9.1 over there, and then I move the 7.65 over to the left-hand side and combine it with the 249.74. So this, and solve for Q, the flow rate is going to be 0.244 cubic meters per second. Incidentally, we could also solve that in Excel and generate a curve that looks pretty similar to our system curve and our operating curve. I wonder if I still have that from a previous semester. Yeah, all right. So let me just show you what I did in Excel here. I have, for a variety of different flow rates, here's the pump curve, and so that was 24.4 minus 7.65 times the flow rate squared. So you can see that as our flow rate increases, then the pump head added is going down. And then here's the system curve, which is 9.1 plus 249.74 times the flow rate. So I've got a variety of increasing pump heads required as the flow rate goes up. And so then I'm finding the difference between the two, because the operating point is when the difference between the pump curve and the system curve is 0. So I just picked a variety of different flow rates, and then when I found one that was pretty close, I did a goal seek to have the difference between the system curve and the pump curve equal to 0. And then it goal seeked this same 0.244 cubic meters per second that I got by solving for Q. So, I mean, I guess this is more work, but it gives us the bonus of being able to graph and see the increasing system curve and the tapering down pump curve. This one, the pump curve isn't decreasing as much as that figure on the slide, but if we had the flow rate continuing to go up further and further, then the pump curve is going down more. Okay, so in this example, we found the operating point, we found the flow rate, then the thing that we need to double check is whether our fully turbulent flow assumption is correct. And so let's take a look at that for the flow rate that we've got. For this flow rate, 0.244 cubic meters per second, then the velocity, if we have Q divided by area, the flow velocity is 4.97 meters per second. And so the Reynolds number we can get from the velocity, diameter, and kinematic viscosity, 1.24 times 10 to the 6th. And then if we put that into the Jane equation, what we'll end up with is a new updated F value of 0.01995. So our original guess was 0.0196. It turns out that this updated value is about 2% different. So I think for our purposes that's close enough, but if we updated this whole thing with the improved guess of F, then it'd give us a slightly different flow rate for the operating point in the system. So are there any questions about the example? Okay, well that's all I have for you today. Remember that on Wednesday is when you've got that assignment for Hardy Cross and water hammer and surge tanks. So let me know if you've got any questions on that one. I'll see you Wednesday.